Good evening, everyone, and welcome to CSOC Small Bridge Design webinar. I'm Jamil Khan and your host for the webinar. I'm a technical director at Beca, Wellington, with over 30 years of experience in designing civil structures. I'm also a national coordinator of CSOC Bridge Groups, and I'm also an active member of various code committees like AS 5100.4, AS 5100.6, and NZTA 3404, nominated by NZTA to represent the bridge designers on this code committee. In 2006, I was a part of the steering committee who worked and developed the current existing NZTA bridge standard bridge design, which is now overdue. Today we have 5 presenters who will be covering the 6 key aspects of the small bridges design. And the aim of webinar is to provide some guidance to the small bridge designer so that the designer can deliver their professional obligation in accordance with the New Building Act and in a consistent manner. And these are the key design aspects we'll be covering. We'll start with the definition and design consideration and criteria for small bridges. Then we'll look at the application of NZTA and other standards. Then we also talk about the guidance to the designer on discretionary clauses from NZTA Bridge Manual or other standards. And then we look in the minimum skill levels and experience expected for the design of these small bridges. In the end, we'll run some case studies, showcase you some of the examples of small bridge designs, different companies or different engineers that did in the past there. Let me introduce our presenters for the webinar. We'll start with Geoff Brown. Geoff Brown is our first presenter. Geoff is a senior technical director with Beca in Wellington and has over 45-year experience in the design, assessment, strengthening, and a full range of bridges across the small river and small stream crossing or big river and the access on pedestrian bridges there. He's also involved in developing the design standard for NZTA and KiwiRail. Our next second is presenter for the night, Nigel Lloyd. Nigel is a principal structural engineer with NZTA. He has 30 years experience of bridge design, evaluation, management, and of highway structures in New Zealand and UK. Nigel is responsible for updating and maintaining the NZTA Bridge Manual, and Nigel was also involved in the design development of a standard bridge, precast concrete bridge beams. The third presenter of tonight is Matthew Ireland. Matthew is a technical director with Home Infrastructure Christchurch team and has over 17 years of experience in the design of the bridges and civil structures. His experience includes design, peer review, assessment, and construction monitoring on road and rail bridges. Matthew also regularly participate in the industry projects, contributing to the design guidance, specification, and standardization design. Our fourth presenter for tonight is Dijan Novaku. Dijan is a structural principal in WSP in Wellington. Dijan has a 39 years of experience of designing civil structures. Out of that, 31 years in working in New Zealand. Dijan utilizes the state-of-art method in his work, and his solution is innovative and effective. He regularly considers safety by design, environmental, and sustainability in his designs there. In the end, Jamil Khan will be covering some case studies for small bridges, showcasing some of the examples of various types of small bridges there. Okay, let's start with it. And our first presenter, Geoff Brown, will start. Geoff, over to you.
So firstly, we're going to talk about definition of a small bridge. What are the characteristics that make up a small bridge? So these are a number of factors that I've identified. So bridges on roads with low traffic volumes or on private land, bridges where the risk tolerance may be different to main highways, structures where the consequences of failure may be lower than main highways. They're usually short, single span, sometimes single lane bridges with spans generally under 15 meters. The design standards may vary from the Waka Kotahi Bridge Manual, and by using either Appendix D to the manual or by designing to AS 1170 and other material codes. And it's worth noting that bridge spans less than 6 meters do not require building consent if designed by a chartered professional engineer. So taking those criteria for what a small bridge might be, they fit into the following categories. So local authority bridges, farm access bridges, private access road bridges, and sometimes simple pedestrian cycleway bridges. Next slide, please, Jamil. Design considerations and design criteria for small bridges. Next slide, please. So the things that you need to consider when you design any bridge, but particularly with a small bridge, are firstly access for materials and construction plant, cranes, and what the lifting weights are going to be limited to. Many of these bridges are located in remote locations on private access tracks, and access can be difficult with large plant and large cranes. The second consideration will be the geometry. What is the length, the span, the width, the lane widths, and the footways that you may need? What are the clearances to streams, roads, overhead utilities? Design life, normally 100 years, but it can be reduced to 50 years to the Building Act. What is the loading in terms of highway, pedestrian, cyclist, horses, cattle, maintenance vehicles? Traffic speeds. If you've got lower traffic speeds, then you can reduce the dynamic load allowance, which reduces the loads. What are the ground conditions at the site? What waterway cross-section do you need to suit the waterway? What are the earthquake design requirements? What is the edge protection? Is it required? Are there any restrictions due to oversized farm vehicles? What are the durability corrosion protection requirements? And is there any need for utility services on the bridge? Next slide, please, Jamil. So turning these into design criteria, thinking first about design life, 100 years is the standard life to the bridge manual. But under the building code, we can reduce that to 50 years, but often we would need to get our client's agreement to that. And a lower design life reduces the wind load, the flood loading, the earthquake loading, and durability requirements as well. Tied in with that is the importance level. For most small bridges, it's likely to be importance level 1 or 2, as defined in Bridge Manual Section 2. And again, the lower annual probability of exceedance you'll have that for importance level 1 and 2, which reduces loads for wind, snow, flood water, and earthquake, which are taken from Bridge Manual Section 2. The road geometry on the bridge itself is normally to the Bridge Manual Appendix A. Traffic lanes are normally 3.5 meters wide, and shoulders vary in width, but down to a minimum of 300 millimeters. If we use Bridge Manual Appendix D, which allows different standards for likely trafficked rural bridges, we can reduce the geometry requirements. And footways, if we have them, would normally be a minimum of 1.3 meters if there's no curb, or 1.5 meters with a curb. Next slide, please, Jamil. Loading. The normal loading for bridges is HN, HO loading to the Bridge Manual Section 3, but that may not be needed. It may not be necessary to design for HO loads, which are the overloads, which are the large vehicles that you see, which use the highways under special permits. So the HN part of the loading covers the normal highway loading, and that covers all the legal vehicles that are allowed on the highway without a permit. If we use Bridge Manual Appendix D for rural bridges, we can actually use 0.85 of HN loading, and we can apply lower load factors for those bridges. Pedestrian loading would normally be 5 kPa, but that reduces if you've got longer spans. Cattle, horses would be covered easily by the 0.85 HN loading. Wind is unlikely to be critical, and with a lower design speed, we can reduce the design load allowance, dynamic load allowance. Ground conditions, we need to understand the ground that we're building the bridge on. So we need some investigation in the form of either a borehole, a trial pit, or scalar tests. We also need input from a geotechnical engineer, or at the very least from an experienced bridge engineer who's got experience of geotechnical engineering as well. The foundations will often be simple, such as spread footings, MSC walls, or steel H-piles, which may be suitable. The waterway cross-section, again, we need some assessment of that in terms of the water levels, flow volume, velocity, to confirm the levels and the span that we require. What is the clearance that we require to the soffit under the 100-year flood Now, the standard freeboard is 600 millimeters. Sometimes that may be reduced or increased depending on the risk of debris. Another question is whether the bridge will be overtopped in a large flood so that it needs to be anchored and doesn't float away. And of course, is the waterway likely to be blocked or damaged? Sorry, is the bridge likely to be blocked or damaged by debris? Next slide, please, Jamil. Earthquake loading. Design is normally to Bridge Manual Part 5, but it is possible to get departures for design for liquefaction, lateral spreading design based on risk assessment. Very small bridges may not need to be designed for earthquakes. If the risk to human life is low, and if they're not going to move very far or collapse, then you may not need to take special measures. And it's worth noting that integral bridges perform very well under earthquakes. Edge barriers are normally designed to the Bridge Manual Appendix B. Traffic barriers may be omitted under certain conditions which are defined in the Bridge Manual. You may be able to use W-section barriers if there are no pedestrians, or at a top rail if you're going to have an occasional pedestrian. If you've got cyclists, you would require barriers normally 1.4 meters high, and for horses and cattle 1.8 meters high, unless the bridge is very low to the ground. You also need to consider if oversized farm vehicles or vehicles carrying oversized loads will be crossing the bridge, because this may limit the barrier height and type. Next slide, please, Jamil. Durability. Design life may influence the choice of materials with respect to durability. Concrete, steel, and timber can give good durability and low maintenance, but timber has a shorter life than steel or concrete. Suitable corrosion protection systems will be needed for steel, unless we use weathering steel, and timber would need to be treated unless we use hardwood. And lastly, utilities need to be accessible for repair and maintenance. It's best to hang them from the side or possibly below the deck. We need to allow for the weight of the pipes and the duct contents in the design. And we can require higher standards for earthquake design if we've got vital services crossing the bridge. Next slide, Jamil. So at that point, I'd like to hand over to Nigel Lloyd, who's going to talk about the application of the New Zealand Transport Agency standards.
Thank you, Geoff. Nice introduction there. I'm here to talk about the various standards that the New Zealand Transport Agency, Waka Kotahi, has for bridges and for smaller structures. They are principally geared towards state highway use and also for local authority road use, but the principles are still there and apply and are can be just as readily used for small bridges. And once you know some of the intricacies of the documents and some of the pitfalls you can fall into, and where you can find options that make it easier for working with a small bridge. And Matthew's going to detail about some of those for you shortly after me. So if we see if I can move. Now, Jamil, can you move it on? It's not moving. Thanks, Jamil. So the Transport Agency has a suite of various documents that are growing. We are adopting standards from elsewhere. We're working with Austroads to get more detailed specifications for structures. But the principal documents that I want to talk about today are the Highway Structures Design Guide and the Bridge Manual. As I said, they're intended for state highway use principally, and also for our local authority partners, but definitely good guidance for yourselves in designing small bridges. Thanks, Jamil. First point of note, Geoff was covering this, that doesn't matter what you do, what size of bridge, it needs in some form or other to be compliant with the building code. The building code it's performance based, and we could talk for a long time about that as well. So without going into too much detail, it's there as background document that you need to be working for and working to. Unlike other forms of structures, there are no standard acceptable solutions or verification methods for bridges as a whole. There are for elements of them, but not as a whole. Therefore, there are options that you're left with of means of designing. Principally that we're talking about here is the Bridge Manual from the Transport Agency. As Geoff mentioned, you could also take the loads from ASNZS 1170 and use various materials design standards from New Zealand. There's the ASNZS, principally Australian standard 5100 for bridge design. That's also just as applicable and appropriate if you can find the right section for yourselves, noting that concrete is designed quite different in Australia than it is normally in New Zealand. And finally, you could find another appropriate design standard. They could be from overseas, say Eurocode or American AASHTO, particularly if you're dealing with certain proprietary standards that might make certain proprietary products, and it might make it more appropriate for you to use elements of those standards. Though there are also the standards that may be more appropriate for the type of structure that you're looking at. I'm thinking particularly of the outdoor visitor standard that's applicable to New Zealand, and Matt will just touch on that briefly shortly. Thanks, Jamil. The Highway Structures Design Guide, it's the overarching document for the Transport Agency in terms of our highway structures design guidance. It doesn't sort of have an awful lot of meat in terms of telling you precisely what to do, but it's got an awful lot of good commentary and telling and pointing in the right direction for certain things. It principally tells you the overall design requirements for highway structures on state highway and local authority roads. It gives an interpretation that the Transport Agency has developed in terms of Building Act requirements, and also how we, as a Transport Agency, view they can obtain compliance with the building code for the structures that you're designing. So it's not only there's bridges, there's retaining walls, gantries, signs, and so forth. So it covers a whole suite of highway structures, but there is some good even fences, but there's good guidance in there for you. The last point that's in there is the technical approvals process. This is geared very much for Waka Transport Agency use in terms of how you want the bridges to be designed. But it is good guidance, and it gives you some real good pointers of the kind of elements that Geoff was just been talking about in terms of things to expect, things to look out for. Elements to put together, such as the form of the bridge. What alternatives are you considered, or have you considered? How are you going to design the bridge? How is it going to be built? So they just pointers for things for you to think through in terms of what are you expecting a bridge to look like, and how is it going to be put together, and then how is it going to be maintained in the future? Okay, thanks, Jamil. Okay, moving on to the bridge manual. It deals with principally with as you might expect, it says what it is on the tin. It deals with the design and evaluation criteria for bridges, culverts, and also stock underpasses, subways, and so forth. With nothing else in place, it's kind of the quasi New Zealand standard for bridge design, but it doesn't have that status, shall we say. It's mandated for any bridge that gets funding from the Transport Agency. So that's any bridge on a state highway, any bridge that gets part funding from the Transport Agency on a local authority road. It's not required and can't be mandated for private bridges. But it's worth noting that it will be recognised by most consenting authorities. These are my words, but as a standard alternative solution. And therefore it is recognised by your consenting authorities. Thanks, Jamil. These are the various sections of bridge manual. I don't want to spend too long on them, but in essence, the key points to look out for there, the design loading, and then pointers and how you're going to go analyze and designing the bridge, and then also specifics on earthquake design and so forth. And Matt will go through some of these elements in more detail rather than me going on about them. Okay, thanks, Jamil. One specific that Geoff's alluded to, the bridge manual, there's a separate section tucked away in the back, a little appendix that's there for likely trafficked rural bridges and other structures. These are the criteria that are used to define which bridges can be designed to meet these requirements without any need for departure. You can go ahead straight away with these. They're fairly restrictive requirements, but you'll find they probably apply to quite a few local authority roads out in the rural backwater. It's worth noting state highways are not specifically excluded, but non-comply, basically because there's not many through routes in those that are busier than the vehicle numbers that are required there. Logging trucks are probably excluded. I don't know specifically why, but I would imagine it's to do with the fact that they're prone to being overloaded. Okay, thanks, Jamil. Specifically, the list of modifications is not that long, but they're here. So they allow you to have reduced width. It could be that you don't need a footway. You can have a narrower than 3.5 meter lane width if that's what's required or is suitable for the environment, particularly a private bridge, of course. Barriers can be omitted, or it may be appropriate just to put something more like a pedestrian rail or even a wooden fence on there, noting that there still is a requirement for the building code for protection from falling. As Geoff alluded to, reduced live load. It's at 0.85 HN. It's worth noting, and the trucks there remind me that this equivalent, it's slightly outdated, but it's equivalent to a class 1 vehicle at 44 tons. Not the new general access vehicle, which is 46 ton, but to get to 46 ton or even to a 50 max vehicle, you're adding extra axles at the end of the vehicle, which is putting the bridge, but in it's making the vehicle longer. So these are effects that aren't going to really of worry to you unless you're designing bridges in a 22 to 25 meter span and above. So for small bridges, it's not going to be a problem. 50 max, sorry, not 50 max, HPMV is a different matter. And if it's possible that you may end up vehicles are serving 50 max, and it could be that the milk tankers are serving a particular, a HPMV route, and it could be the milk tankers are serving a HPMV route, then they need to be designed to a different loading because they have a heavier individual axle load. Appendix D gives you some different load factors and combinations, less conservative, lower risk, and therefore there's some benefit there for smaller bridges, some less onerous crack widths in concrete, and that's about it. But it's worth noting that there are other factors in the bridge manual that are deal with the reduced scope that you have of a smaller bridge. That can be, as Geoff has alluded to, and Matt will give you some further details in terms of the importance level of the structure. It means you're designing for a smaller return period of design event for earthquakes, floods, and so forth. And then also there's always a scope for departures, and that's something that Matt's going to cover in much more detail in a moment. So thanks, Jamil. And with that, I'll hand over to Matt.
Hi everyone, and thanks Nigel. Hey, so I'm here today to speak about guidance to designers on what clauses of the bridge manual are discretionary. But first, before we really get into that, we just need to talk about, well, I'm going to revisit a few things that Geoff and Nigel have already covered, and just expand slightly on some of these. So compliance with the Building Act. So bridges, they're classified as ancillary buildings to the Building Act, and therefore must comply to the building code. So there's B1 structure, B2 durability, and also possibly F4 for falling from heights, and potentially some others depending on your structure. So as was alluded to earlier, so there's kind of three possible ways to achieve compliance. So there's the verification methods, so following the design standards like NZS 1170 and the material standards for concrete, NZS 3101, steel 3404, and the timber standards. As Nigel kind of mentioned before, there aren't, well, another possible way is acceptable solutions, but there aren't really any that are suitable for bridge structures. And so that leaves us with the third option, which is alternative solutions. And so the key with an alternative solution is that it needs to achieve compliance with the performance requirements of the building code to the satisfaction of the consent authority. So thanks. Next slide, Jamil. Thanks. So as Nigel's already touched on, so more often than not, bridges, they're designed as an alternative solution, and the basis of that alternative solution is the bridge manual. So it has been prepared and to be an alternative solution for clauses B1 and B2 of the bridge manual. But however, it's not the only option. And so I'm just going to touch on some alternatives on the next slide. But first of all, again, just wanted to reinforce the point that if you're looking to understand a bit more about bridges and your compliance pathway to the Building Act, you really should download the NZTA Highway Structures Design Guide. It's available freely on NZTA's website, so it's a great resource. So, Next slide, please. So again, possible alternatives to the bridge manual. So for the really simple structures, it is possible to use a verification method approach using the 1170 suite of standards and the material standards. But then most of the time we will end up needing to go down the alternative solutions approach. And so what are some alternatives to the bridge manual? So already touched on earlier. So the track and outdoor visitors structure standard is one that we see pop up sometimes. So that's SNZ HB 8630. It's actually quite a useful document. It was written to help dock with the walking and access structures on their tracks. It is, it's a 2004 document, so some parts of it are a wee bit out of date now, so it could do with an update, but there's actually still some really useful information in there. So it's worth a read, and we'll actually show a couple of examples at the end where the design basis for the alternative solution was using this document. Another option is to adopt part only of the bridge manual, and sometimes we might see this. So essentially using a verification method approach, but essentially you could be using the bridge manual for the design vehicle loading, say, such as the lightly trafficked rural bridge requirements of Appendix D, which Nigel was discussing just before. But then there's other times where we might actually need to use a different alternative solution instead of the bridge manual. So if you read the scope at the start of the bridge manual, it kind of clearly says that it doesn't cover cable or suspension or cable supported or suspension structures. So if you've got one of those, you're going to need to look for a different guidance document, which will probably come from overseas. And then also if you're looking at alternative materials as well. So one example here could be, say if you're designing a structure that was fully made of, say, carbon fiber composites or something like that, you'd have to go looking for some appropriate guidance to base your design on. Next slide, please. So now to get to what clauses of the bridge manual are discretionary. So ultimately, you may choose not to use the bridge manual at all. So again, there's some disclaimers there. So if NZTA is providing the funding, that's probably not going to be an option. But if it's a private structure, you've got a bit more freedom. But most importantly, really, you need to document your intended compliance pathway well. That's so that any reviewers can understand what you based your design on, and also the Building Consent Authority. So the key thing there is that any alternative solution must achieve compliance to the satisfaction of the Building Consent Authority. So at the end of the day, they're going to be the one making the call there. Also, as Nigel kind of indicated before, more often than not, bridges, even if they're designed to the bridge manual, they won't won't meet all the requirements of the bridge manual. And this is often covered in a departure process where essentially you're agreeing with the asset owner that you won't meet particular clauses of the bridge manual. This might be because some clauses are just not suitable for the context of the project or the bridge, or they might just be a bit too onerous. But ultimately, you need to agree these with the asset owner and again, document them. So the likes of NZTA, obviously they deal with this on a day-to-day basis, so they've got procedures and processes in place. But if you're looking at a small kind of private bridge, then in your design report, you just want to document that and and discuss and clearly explain it to the owner, the basis for it. So next slide, please, Jamil. So now just to go to building consents. So for bridges, a building consent may or may not be required. So there is, within the Building Act, there are a number of avenues for bridges to be exempt from building consent. So Geoff kind of touched on one at the start there. So for bridges less than 6 meters long, along with some other conditions, there is a section in the Bridge Act that specifically includes or exempts these from building consent. But that's not the only avenue. So there are a few others. But at the end of the day, the fundamental thing is that compliance with the building code is required irrespective of whether a building consent is required or not. So that's the key thing. And also the asset owner will need to engage a suitably qualified chartered professional engineer to design or review the bridge design, whether it's exempt from building consent or not. So next slide, please, Jamil. So now just to get into just a bit more of an overview of some of the specifics of the bridge manual. So again, we touched on this earlier, that the default in the bridge manual is a 100-year design working life. For a private structure, you know, a 50-year design working life may be more appropriate or suitable, you know, to make some savings. So the benefits really of reducing the design working life include reduced durability requirements. So that could be concrete covers, corrosion loss allowance for uncoated steel elements, and also if your structure's using timber, because within the New Zealand standards, the timber durability is only really covered up to a 50-year design life at the moment. So it just makes it a bit easier to fit within those standards. Another benefit of reducing the design working life is a reduction in the return periods for design actions. I'm just going to cover that in a bit more detail on the next slide. Another thing with the bridge manual is that the default for protective coatings for steel elements is a 40-year life to first maintenance. So again, this could be reduced. Typically, you'd probably go for a 25-year life to first maintenance if you're going to reduce it. Again, that could make you some initial cost savings, but in the long run, it may not. Next slide, please. Cool. So now just revisiting importance level. So again, depends on which compliance pathway you choose. If you choose the bridge manual, you'll be looking at table 2.1 of the bridge manual. And if you're choosing an 1170 type approach, you'll be looking at table 3.2 from 1170.0. So just to highlight a couple of the key differences between the two, really. So in 1170, it does give you the different annual probabilities of exceedance for the different design working lives and importance levels. But in reality, there's actually not a whole lot of difference between the tables. A few revisions ago in the bridge manual, they actually pegged back the annual probability of exceedances for the environmental effects, so wind, snow, floodwater actions and seismic, to be equivalent to that of a 50-year design life. There's one exception there, which is really the IL or importance level 1 structures. Within table 2.1 of the bridge manual, these are still actually based on a 100-year design life if you do a comparison to the 1170 tables. So potentially, and for the structures that we're talking about today, they can fall into the IL1 category. There could be a saving if you adopted the annual probabilities of exceedance from 1170. But in saying that, obviously the bridge manual was written more in the context of buildings and 1170 on bridges, and 1170 is written more in the context of buildings. So the likes of the 1170 tables don't provide annual probabilities of exceedance for floodwater actions. So you're going to end up probably referring back to the bridge manual for guidance. Cool. Next slide, please, Jamal. So now just to briefly go over seismic design. Again, depends on which compliance pathway you choose, but what we're just trying to highlight here is that the bridge manual adopts significantly modified seismic design procedures compared to New Zealand standards. If you look at chapter 5 of the bridge manual, it's nearly a 70-page section, so there's actually a lot of information in there. But the fundamental difference really there is that the bridge manual includes a series of performance-related criteria related to post-earthquake function, repairability, and acceptable damage, which are required at the different limit states. And so the bridge manual, a wee bit different from 1170 again, it also outlines its own performance or limit states. So we've got an SLS term, which everyone's probably familiar with, but the bridge manual defines a damage control limit state as well, which is essentially equivalent to ULS under 1170 approach, but it includes the additional performance criteria for the post-earthquake function, repairability, and acceptable damage as defined in table 5.1 on the left. Probably a bit hard to read there. Again, there's a collapse avoidance limit state in the bridge manual as well, which is roughly equivalent to an MCE case from 1170 with the additional performance criteria. So next slide, please, Jamil. So some more things from things about seismic design in the bridge manual. So the bridge manual, it adopts a preference for a displacement-based design approach, which is a bit different from the normal New Zealand standards. And also, whilst the design spectra for seismic demands is based on 1170, the actual to determine the design spectra is quite different. There's a number of different factors built into the bridge manual, which you'll need to work through. For potential plastic hinge zones, also in the bridge manual, these are based on probable strengths for materials, and there's a number of specified strain limits to consider as well for plastic hinges. And then once we get into the material requirements as well, the bridge manual provides additional kind of requirements over and above the material standards. So one example here is the reinforcement detailing requirements. The bridge manual has some kind of tighter spacing requirements which need to be considered. Also with bridges, soil structure interaction is, quite often a fundamental consideration. So within Chapter 6 of the bridge manual, where you're considering liquefaction and lateral spread, there's a series of scenarios which are outlined that you need to consider related to considering inertia with liquefaction and lateral spread. But ultimately, what we're just trying to highlight here is that the bridge manual approach is quite different to 1170.5, but if you're designing a really simple structure, some of the requirements from the bridge manual might be a wee bit onerous for these really small bridges. So next slide, please. Cool. A few other of the more particular requirements, just a really high level overview. So section 4 of the bridge manual includes quite a few specific requirements for detailing and material requirements. So one thing that you might see pop up is the requirement for settlement slabs. Obviously, if you're not on a public road, you might decide that, you might agree with the asset owner that these don't need to be incorporated. Again, Geoff's already touched on the geometric requirements outlined in Appendix A. These outline, for public roads, really, the lane and shoulder widths that you should design to. If it's a private structure, again, you've got a bit more freedom to choose yourself. There's also a number of kind of loading requirements in the bridge manual, which you could consider. So Chapter 5 of the bridge manual now includes tsunami loading requirements. For small bridges, again, you probably wouldn't be considering these because they're quite large loads. And then there's kind of serviceability criteria as well. So one such example is the vibration due to traffic. Again, might not be critical for these small bridges, and you can agree with the asset owner not to meet these requirements. Another thing that the bridge manual is starting to introduce is low damage design principles. Again, for these really small structures, you probably don't need to consider them. So next slide, please. So just to touch a bit more on barriers again. So Appendix B provides the requirements for traffic barriers on bridges, and also does cover pedestrian barriers for highway bridges, really. So we've kind of touched on this a wee bit earlier, but there is a no barrier option. But in reality, there are 8 conditions to satisfy there to ensure that a no barrier option is appropriate. I'm not going to read through all of these, but at the end of the day, it's pretty difficult to satisfy all 8 of these criteria. So therefore, particularly on public roads, the no barrier option will only occasionally be used. And that even also applies to private structures. It's probably going to be quite uncommon to use the no barrier option. So next slide, please. So what type of barriers are kind of appropriate for private bridges with no public access? So one of the key considerations is traffic speed as well. So if you've got high-speed traffic, you may want to consider bridge manual compliant traffic barriers, but for these small structures as well, these requirements are quite likely to be quite onerous. For low-speed environments, what you probably more often will see is the adoption of a robust curb, kind of like the bottom right picture there, or wheel guard with a pedestrian barrier. So to achieve building code compliance, if the potential fall height is greater than 1 meter, you will need to include a pedestrian barrier or guardrail. And another key thing to note there is that there are different requirements for these barriers. So particularly if your bridge is in an area which is likely to be frequented by children under 6 years old, you'll need to adopt the anti-climb provisions, which basically specify some tighter requirements for guardrail design, really, or barrier design. And again, as we touched on earlier as well, if you're designing these bridges in a rural type setting, quite often the local farmer using the bridge will have their thoughts as well on what's appropriate for their stock, and also some of the farm equipment gets quite large as well. So you need to consider that to make sure that that can actually fit across the bridge. So that's just a bit of an overview from me, and I'm going to hand you on to Dayan.
Thank you, Matthew. And thanks, Jamil. If you don't mind continuing with the slides. You already introduced me. Just Darren Doriguzzi was the co-author of this part of presentation. Yeah, thanks, Jamil. Next slide. So without repeating most of the stuff which was said, also stuff was discussed previously, and I might just add a few more things and refresh again here. So first, to start with TAs and consenting requirements. So whether the bridge is exempt from consent or not, the territorial authorities may or will require a producer statement PS1 design from a chartered professional engineer. So the all bridge design must be supervised and signed by a suitably experienced bridge engineer. In considering whether to accept the producer statement, the council or TAs will normally assess the credentials of the auto, ensure that the person has appropriate experience and is practicing within their field of expertise or practice area. Next slide, please. As I said, they'll be suitably qualified to sign PS1 or any of the other PSs, which will come later. You must have your practice area must include bridge engineering or bridge design. If the bridge is deemed sufficiently complex, the TA may require producer statement PS2 design review. So that might be internal or external, it depends. And the same requirement as for PS1. Council also may or will require producer statement PS4 upon completion of the project. And again, the same requirement for person signing it. Next slide, please, Jamil. So producer statements have no legal status under the Building Act, but how they are accepted as a primary means, to determine building code compliance, which we mentioned a few times, is a must. Definition of the practice area which you should have if you're signing one is defined, and you can find that definition on the right, but if you can't read it, you can always go to the Engineering New Zealand website and find the definition and the requirements there. If you're chartered, you already know that. So there's nothing new here. Next slide, please. So the Building Act also sets a 10-year long stop traditionally limited civil lawsuits to 10 years from the act of omission. So that we'll probably remember a few things when that was used. I won't mention the case, but about 10 years ago or more, 12, 14 years ago, following an earthquake. A court decision in December 22 regarding damage from the Kaikoura earthquake has set a precedent that engineers can be pursued for liability beyond 10 years. So next slide, please. So, and these are some wording about the liability indemnity period, which you can also find in the Limitation Act. So that's probably, don't want to scare you too much, but something that you should consider in your design and before making bold decisions. Next slide, please. Example how, again, not wanted to scare anybody, how the things went wrong. Many years ago, well, about 20 or 30 years ago, sorry, a bridge collapsed, and it's famous, the Berryman case. That was a bridge, suspension bridge, which was across the Returuke River in Kings Country in New Zealand, built on public road for nearby landowners, the Berrymans, by New Zealand Army, who did design and construction, using materials provided by the family, by Berrymans. So Douglas fir was used for transoms on the bridge instead of specimen tenons, radiata pine, macrocarpa, with the Berryman signing a statement taking responsibility for the change and subsequent inspection and maintenance of that component of the whole bridge. On the 22nd of March 94, 2 transoms due to decay snapped while light truck was actually crossing, resulting in a driver's death. So the first inquest to collapse was in 1997, with final settlement in the Court of Appeal in 2008. So 14 years to go. So you can imagine what how the involved felt about 14 years of their life being spent on that court case. So just something to be aware when you are making decisions and asking for departures and whatever. Next slide, please. So what are the skills and experience that you must have other than having a practice area, obviously, so you can sign PS, produce statements. So the must-have skills, obviously, if you are doing that type of work, is familiarity with the building code. And also with a bridge manual, if you are using bridge manual, even if you're not going to use a bridge manual, you have to know why you are not using it and where are you departing from it. So, and also on other NZTA documents like highway structures, probably, if you're not using bridge manual. You must be familiar with the New Zealand loading standards, for example, NZTA 1170 parts, and as Matthew said, also with New Zealand material standards, timber, steel, or concrete. Next slide, please. What are nice to have, as they call them, skills experience? It's a sufficient understanding of geotechnical engineering issues. And in all these, I didn't say you should rely really on advice from those whose practice area is in that area. You shouldn't make decisions on your own. You should know a little bit about hydraulic issues, if that's the problem at all. Geometric design, again, if you want to ask for the departure, you have to know why and what departure you're asking for, and some understanding on environmental issues which might arise. Next slide. So in addition to what Geoff nicely covered, what you consider in your design, I'm just going to repeat it again. Consider constructability. So capability resources available to the contractor, remoteness and access to the site. Consider details that are easily accessible for inspection and maintenance. If you're, for example, using timber, pressure treated timber next to the concrete, separate them, to make the life longer. Consider departures that eliminate the need for vulnerable, hard to inspect repair details. For example, whether you need linkage bars. If you have a single span small bridge, which is well confined with abutments, generous seating, which will prevent unseating, then you probably can go without the linkage bars, which are typically difficult to inspect. They are prone to damage, and they are almost impossible to replace. So if the seismic design is required or consider using capacity design and good detailing. That's always useful. You're probably all aware that seismic hazard or seismic risk or both can change with time. So make sure that you sort of a little bit future-proof it, your design. Next slide. Thank you. And that was me. So thank you very much. I pass it on back to Jamil to show us some case studies of the small bridges.
Sorry, Jamil, you're just on mute.
Sorry, apology. Thanks, Dan, for it's a so in the this is the last section of our webinar where we're going to showcase some of the examples of the small bridges, and we show you how the idea is to demonstrate that what we talked about a lot during last 1 hour, where we've been implemented on those examples there. And these we collected a different type of bridge examples. So we start with the road bridge examples, which is a local road or remote area road with less traffic. Those classes were small. Then we will move to these cycleway pedestrian bridges with light traffic. Then we give an example of those small bridges like in the timber bridges in the golf course and other. And then we'll talk about some of these farm bridges there. So first example I'm taking is in a Kaikoura, and this was rebuilt during the after Kaikoura earthquake. It's a Glen Bridge, and again this is low traffic volume this area, but the design life was 100 years, and importance level of structure was level 1, and traffic load is designed for full HNH loading. Span length is about 10.5 meters, and provided the TL3 barrier. The bridge structure, superstructure, consists of the integral steel composite bridge, okay? And the foundation is driven UC piles. But again, the departures were applied for the freeboard because we didn't have the freeboard much way. And then the other approach is departure apply for that one. This bridge was designed by Holmes Group, and it was built in 2020. The next example I've taken is Milling Road Bridge. As again, design life is 100 years, and an importance level 1 because of the low volume traffic classified. And the traffic loading which we adopted the Appendix D, where is a 0.85 HN loading. This class 1 span is 14 meters. On this bridge, there's no barrier, but the timber rail is provided. Timber railing is provided there. Bridge deck is a prestressed double T beam. Foundation was a shallow piles, which was placed using excavator during construction. And the departure was applied for the loading, barrier, and seismic design. This design was carried out by WSP and was built in 2002. This is an example in the Farura Stream Bridge, which is in Queen Elizabeth Park in Wellington. It is again, it is a very private access for this couple of the farmers on a site there, and it's and it is a control access there. It's a low speed environment. Again, structural importance level was 1, but the structure was designed for the full HN loading. Span is 12 meters. The barriers is provided as a timber as a concrete curve with the livestock the friendly barrier, which is a railing, and that was the owner said if we discussed with the owner and or provided they needed this type of the railing for the cattle to carry over. And again, the bridge design deck superstructure was a hollow core, simply supported on an abutment, which is cast on the top of the driven sheet piles, and sheet piles was drive to the set. And again, the departure for this bridge was applied to the authorities for the barriers and the seismic design. It was designed by Beca, and it was built in 2019 to 20. And I think during construction work was carried out during when we were hit by COVID. The next type of the bridges we're taking is the cycleway bridges, cycle bridleway and walkway part. This is these example I've taken is from Mackay to Beca Expressway bridge, where we have a express project where we have a 3 similar types of bridges there. So the bridges we use for the pedestrian, cyclist, and carrying the horse and rider. So again, the importance level was 1, and design life is 100 year. Loading was only pedestrian loading and light vehicle loading, because agency wants to use for these bridges for the maintenance vehicles only. It's not a public access. It's only for public access, but not the public vehicles, but only for the maintenance purpose. They want to carry the maintenance vehicles. So we use a lightweight vehicles loading. Spans were about vary from 20 to 22 meter. The structure barriers was just because it's a steel through truss barrier. So trusses act as a barrier and railing, and which is 1.8 meter, which meets the requirement for the cyclists and horse riders and item. Bridge deck is a through steel trusses with the composite with the concrete deck at the bottom. And the foundation was an MSC wall, the shallow foundation, with the MSC wall barrier. The loading departure we applied for the loading barriers and seismic, and so this one basically, this is one example. This structure was not designed for any seismic, and there was an area for liquefaction. The understanding with the client was that if the earthquake liquid happen, the bridge will move, and then they can reinstate this one as long as because it's not as a critical access required during the earthquake, and then it'll move, and then they can bring back and bridge and later after in a post-earthquake. It was designed by Beca and it was built in 2015 and 16. The similar type of the bridges was the part of the shear path bridges, which is part of the Beca to Kotahi Expressway in Wellington. Again, the design life is 100 year and importance level 1, and the loading was a pedestrian as lightweight vehicle, because this shear path is a continuation of the CW path of the from Mackay to Beca, and it goes to up to the from Beca to Levin. The barrier are galvanized steel rail with the friendly cyclist friendly and cyclist friendly, and the structure deck super deck is consists of 400 deep hollow core simply supported. Foundation was shallow driven steel piles. Again, the departure for this type of structures will apply for the loading barriers and seismic design. Again, it was designed by Beca and was built in 2021 and 22. Next example is another shear path bridge in Blenheim. So now Opera River Cycle Trail, and again the design life is 100 year. Importance level is 1. And loading is a pedestrian cyclist, and using the other we mentioned earlier the code at HB 8630-2002. Span is 12 meter, and the barriers are part of the galvanized through trusses with a small mesh in between to comply with the F1 requirement of the Building Act. The bridge deck was FRP mesh. This is another example we mentioned earlier that if you're using a different material, and then on this job they use a different designer use different material, but then they use a different standards, which because this type of material is not covered in the bridge manual or the other New Zealand standards. Foundation is a short driven steel pile. Again, the departure for this one was applied for loading barrier and seismic. So this is the example that if these sort of a structure, if you're not D2 design for the seismic, design was WSP and it was built recently. The next example we pick up is some golf course bridges. So this example is a 50-year design life, and for again important structure is level 1. The loading was taken 4 kPa from HB 8630, and a specific golf cart and a maintenance vehicle. Golf cart maintenance vehicle, and span is a 6 meter. For the bed, there's no barrier but timber curb and rail. The design is a timber steel deck is a steel timber beams and planks, and foundation is a timber post with a concrete footing. Again, this departure from the standards of the loading barriers and the seismic design. This was designed by Holmes. Another example of these golf course bridges is Royal Wellington golf course bridges. Just again here, designer agreed with the client. The design life was 25 years, importance level was 1, and the loading was agreed with the client that the maximum 10 people can cross one time with 100 kg weight, or the golf court with the 2-person and bags. So these are the limits, and that's what they have put a signs on those limit there. And so its span is again 6 meters. So there was no barrier when there's a drop is less than 1.5 meter. As you can see in a photo, there's one is photo without barrier. We have the timber curb, but no rails. The other one is a drop was more than 1.5. So the timber rails were provided for the pedestrians. And they found the deck is a timber beams and planks, and a timber post foundation is considered timber post with a concrete footing. Again, departure from the standards is a loading, because the specific loading was agreed with the client, and the barrier requirements seismic run. This was designed by Beca, and it was built in 2012. The other example, the farm bridges, courtesy to Bridget, New Zealand. So we took the 2 examples from their website, and they have 2 examples which are farm bridges. They have a number of examples, but I pick up the 2 examples. One is the 14-meter span, which was built in 2018. Another one is the 18-meter span, which is built in 2022. They have a similar apart from the spans, the criteria was similar for both bridges. Importance level 1, and the loading was adopted is 0.85% of HN loading. The spans, as I mentioned, is a 14 or 18 meter. The barriers are concrete curb with a galvanized steel railing. Bridge deck is for both bridges is a prestressed concrete double T beams, and foundation is a steel driven piles with a precast abutment. I couldn't get to what are the departure they have applied, but again, the design is a Bridget, New Zealand, and designed by subcontracted to the Taikit engineering consultant, and it was built in 2018 and 2022. I think with this one, we have come to the conclusion where what we want to cover in this webinar, and now we have a time to answer your question. Those questions you have populated in your chat there, and we will look at the answer there, and we will utilize this time to answer the question. If we could answer all the questions, then we will be providing the answer on a website. And so now is low design life. Lower design is 1 is 100 even down to the 150. 1 is to 50 year design standard, means that less over engineering. However, if the bridge is still to be 10 to 20 years after the 50-year design life, do we need to consider our design or apply the strengthening if a more cost-effective extension of life is replaced?
So that's a question for me, is it, Jamil?
Yeah, the question is, you say the requirement is that whether we need to design 100-year or the 50-year design life, but what happened during the life of 20, like life of the bridge, which is 100 to 50, 10 to 20 years time, if we hit by the 50-year cycle events, then do we need to consider that one to replace strengthening or replacing them?
Right, I think the answer to that is that if you're designing for 50 years, you design for 50 years. Most bridges will extend beyond that design life, but they will require to be maintained. And of course, there are 2 aspects to the design life. One is the durability aspect. And of course, most materials would need maintenance during the design life anyway. So even if it's a 100-year design life, you're still going to need to maintain the bridge at intervals during that time to get the 100 years. If it's 50 years, the same applies. The other aspect of that is that by adopting a lower design life, you are reducing the loading because of the exposure time comes down. So from a risk point of view, the loads will be lower due to environmental effects. But in terms of extending it, I think that's not necessary. I think what would happen if you design for 50 years, and then as you get towards the end of that time, if you want to keep the bridge longer than that, you would need to do maintenance. You might need to do some strengthening because the materials might be worn out or the loading might have changed in that time. So it's very likely that you'll get towards the point where you need to do something to extend the life of the bridge. But I think it's better to leave that until you get to that time, rather than trying to preempt that at the original stage. Because if you're going to do that, you might as well design for 100 years full stop. Okay, Jamil?
Thanks, Geoff. The next question is, so the atypical challenge is sometimes determining the importance level of a small or insignificant pedestrian bridges. Oftentimes is IL2, as per the New Zealand NZTA bridge manual, is not appropriate. Any thoughts on that one?
I'll throw that one in. It's a good question. The bridge manual really is dealing with, when it talks about a footbridge, it's mostly thinking of bridges that are likely to be crossing a major highway and so forth. So I think for these smaller bridges, I mean, Jamil's put some worked examples up there of bridges that are, I would say, come into that category, and they're most likely designed for IL1, and I think that would be appropriate. So it's something for us to take away in terms of what's put in the bridge manual in the future, but I would say certainly question that, put it forward to your client, also the consenting authority, and promote an IL1 solution if that's appropriate.
Thanks, Nigel. The next question is that for prestressed bridges, what class would a small bridge be, like it for the crack width, etc.?
Shall I have a go at that? I mean, from a design perspective, whether it's a small bridge or a large bridge, if you're working to the bridge manual, which then takes you back to the concrete code, or you're not working to the bridge manual, you're still going to be applying the concrete code, and the crack widths are defined in there, and they don't really distinguish between a small bridge and a large bridge, I think it's fair to say. So I'm not sure that there would really be any difference in terms of the crack width requirements. I mean, they're mostly around durability. That's the reason we manage the crack widths. And if it's going to last 50 years, it's still a long time. So you need to be thinking about the durability of the concrete and the risk of corrosion. So I don't think that is something that would vary between a small bridge and a larger bridge.
Okay, thanks, Geoff. The next question is, what is, sorry, Nick, just keep on refreshing this one. Sorry, our next question is, I need to know what are the other consideration for alternative materials such as aluminum. Do you have any standard or example in a bridge manual?
The bridge manual covers aluminium, but it really is a very brief section referring you to the appropriate Australia, New Zealand standards. On top of my head, I can't remember them, 1664, I think. There's not a lot of guidance in there, but it's an emerging field. There's a question later on that I'll kind of sneak in. There's a similar question about timber, and again, an emerging field. We're very much looking now as an agency to increase use of timber, particularly glulam timber. So certainly in the timber field, there's going to be increased guidance coming. Aluminium, it's coming into the market. It's certainly in the small bridges that there's interest.
Thanks, Nigel. The next question is an advice on appropriate geotechnical investigation for a small farm bridges. Oftentimes private clients can't fit the bill of significant investigation testing. What is the consideration appropriate to and cost-effective testing for these type of structure? Is a departure from the NZTA bridge manual requirement for the geotechnical testing acceptable?
Shall I answer that first?
Yeah, sure,
maybe Nigel might want to add something. I mean, my feeling is that any bridge, you need to understand the ground, whether it's a small bridge, a big bridge, or whatever. But the extent of investigation will depend on the risk that is there. So that's where the experience comes in. So if you're looking at a bridge site, if it's low to the ground and it's on the banks of a stream, for example, you need to understand whether the ground is going to be soft, and you're going to get settlements, whether it can stand the bearing pressures. So for that, you're going to need some investigations. I can't think of any situations where you would just blindly build a bridge without understanding what you're putting it on. So that is really the key thing for me. I think when it comes to departures, I doubt that you'd ever get a departure to do no investigation, but obviously the degree of investigation might vary depending on the scale of the bridge and the risk that is involved in that particular structure. Do you want to add anything to that, Nigel?
No, I think you've covered that. I mean, the only bridge I can think of that I would be put in without ground investigation is a Bailey like behind me in times of war. So it really is, think about it. Even if it's the most basic of tests, just to make sure that the ground is going to do what you're wanting it to do and you're expecting it to do.
And that's where the scalar test comes in. That's a very low cost, easy test to do. You can do that at any site, and you're going to have an idea what you're building on. And even every house we build will have a scalar test somewhere along the way. So I think that's a very minimum. Beyond that, you might do a trial pit, maybe at each abutment, or maybe just at one abutment. And if you've got very difficult ground conditions and a lot of soft ground, or you're not sure what the bearing strata is going to be, that's when you'd start to go towards boreholes. But I think it's a good point. But when you're dealing with a private client who hasn't got a lot of money to spend on it, it can seem like a lot of money to spend on just an investigation phase, and it is a problem that we have encountered.
Thanks, Geoff and Nigel. The next question is, Geoff mentioned that very small bridges may not need to be designed for earthquake. The question is that what regulatory pathway do you suggest is taken to justify this while it's still complying with the building code? Thanks.
Do you want me to talk to that first?
You talk to first, and then I think Matthew can.
I think Matthew touched on this as well, but certainly in our experience, there are situations where we haven't really designed for earthquakes per se, but we are making sure that the bridge, if the earthquake happens, like the bridges at Beca to Peca, those footbridges, we know the bridge is going to move, but the consequences of it moving are relatively minor. The bridge is only a couple of meters above the ground. It's on foundations that will allow it to move maybe 0.5 meter to 1 meter before you got any chance of it being falling off its supports. So I think the risk is relatively low, and that's the approach we took on those when we sought a departure for that. So we know that it can be done, but there's not many situations where you can just ignore it entirely. I think it's fair to say.
Yeah, so I think it's considered, and low importance levels, the seismic design criteria are going to be very low. But again, as Geoff highlighted, you can, to a certain extent, on some of these really simple structures, you're making a judgment call where it's not going to be critical. So.
Thanks, Geoff and Matthew. Sorry, I need to go back in on top of the. Okay, next question. Is there any difference in the design principle while designing a new small bridges and assessing the existing small bridges? Like we can use the NZTA for the seismic assessment of the building to consider the probable strength instead of the nominal strength.
I'll start that one if anyone else wants to chip in.
Nigel.
But yeah, the assessment loading in the bridge manual was updated not too long ago, and it's a bit more complicated than it used to be, but ultimately the assessment loading is basically the same as you would now apply for an Appendix D loading of 0.85 HN. And that equates with everyday traffic, your 45 ton admittedly, but your heavy everyday traffic on public highway. So there's not an awful lot to be gained there. You may gain a little bit by using some slightly lower load factors and different load combinations. I'm not sure that I see a great deal of benefit in that, but ultimately it's just down to assessing the risk of the structure that you're looking at.
Nigel,
Sorry, go Dejan.
Yeah, thank you. Nigel, I think the question might be not only related to live load, but also seismic, because the second part is there. So you want to comment on that from the NZTA point, and I can probably say what I think.
I think they're also talking about the problem material strength, like an NZTA requirement. I assume the bridge manual allows that one. Can someone?
I'll let you answer that. I'm not an active.
Okay, Dan.
If the question is seismic assessment, I mean, there's some guidelines of seismic assessment in the bridge manual, but basically, we use NZTA guidelines for assessment of buildings, and also the other references like Priestley book, the seismic assessment and retrofit of bridges. So that's all defined in this document. So no reason to be, as for big bridges, small bridges, I don't see the reason why I should be following something else. Typically, the demands on the small bridges will be very small, because they're small bridges, they're light usually, or short spans or whatever. So That's my view.
And also,
Thanks, Daniel.
just to expand on that question a wee bit as well. So they're talking about probable material strength. So I think in the first instance, Chapter 7 of the Bridge Manual's got fairly good provisions of, you know, what material strengths that you should use for the different materials based on their age for the starting point. But it also has additional provisions if you want to go a step further as well. So it's fairly well covered in Chapter 7.
Okay, thanks, Matthew, Dija and Nigel. The next question is, can the local government authority provide a departure to the criteria for rural bridges set out in Appendix D? For example, increase the AAD requirement till it used for to still use Appendix D.
I'd say yes.
Yes, because
that's down to the local authority to how far they're willing to accept a departure. I mean, a road with 150 vehicles per day, fine. A road with 1,000 vehicles per day, no. So it really is. It's down to the authority to assess the risk, and if it's a departure, it's likely that the transport agency will get involved as well. So it's a value proposition. If it really is a significant saving as a consequence, then yes, we'll look at it.
Yeah, thanks, Nigel. The next question. Interesting to know a cost difference of bridge design option for a light vehicle versus a heavy truck bridge, and a standard requirement to retrofit the bridge for a modern light loading. A lot of backwater Taraki road bridges and logging truck and etc. exceed the limits, and interesting to know your thoughts. I'll say that this is out of the context of this seminar. We are not in a position to comment on the cost today. We are here to just provide a guidance on the design one. So we will not be answering this question. Thanks, sir.
Jamil, do you want to if you just switch from most recent to most upvotes to some interesting questions there? I think a number of people would like to see answered.
Sorry, it's most recent to most. Oh yeah. Okay, there's got it. Okay, now the question is that team, I have designed a couple of small bridges. Bridge with 85 HN loading for a new subdivision of farm access. I do not have the bridge designer endorsement on my practice area statement. In my S3 assessment, I asked it to include and it to provide us samples, but it seems to be that they could not give me the freedom to do a large bridges. Should I push for this change of the practice, or I stick with the small bridges design without it?
I think Michael's already answered that one well there. It is down to code of ethics and where you feel competent. I mean, ultimately, we all have to start at some level, and therefore it's about designing and then doing so with the oversight of a more experienced engineer as appropriate until you get those skills. And there's at some point in time, you're going to be putting down that you can design bridges, and you decide that yes, I can design small bridges. Great. If you didn't, then eventually you'll be able to design larger bridges. So I just encourage you to be just mindful of your responsibilities. Good answer, Michael. Thank you.
Thanks, Michael, for the response. The next question is the less popular discussion on opinion. And they say that let us talk about the PS2 review of the couple of minutes. A PS2 review suggests to review the work executed by a peer, an equal and knowledgeable experience, qualification, and certification of the design. But more often not, PS2 peer review is not the constructive process, but on where the peer reviewer pokes the holes in the design work. Why is that, and why we do not work together as engineer? Why does the reviewer have to have the final say when the designer issue a more important PS1 certificate? Who has the final say? Ideally, the process should be the collaborative, but more often it is not the one-way street. It is a one-way street where reviewer has this is the final say based on the experience. Why is that? I think it's the best thing is that we in our experience, we that best we think you start peer review from the design, involve peer review in from very beginning and take the journey throughout that one. And then in that case, both peer reviewer and the designer, they are in the same page there. It always be difficult when you designer finish a design and he pass over to the peer reviewer and he was checking this thing and he was not familiar with how you write. And so the reason is comes in. We came out similarly used to become out, but now I think people are understanding that. And when our experience is that when peer review start from the beginning, you have a less hassle free, and the peer review you get a value for the peer review there. Anybody wants to add to anything on that?
Oh, I'm probably just saying probably from our experience, I'd say that's the exception, not the norm. I think generally we find peer reviewers quite constructive. So.
And I don't think that's necessarily peer reviewer is the final word. You know, it's designer is the designer, and he knows everything from A to Z. Peer reviewer might be missing something, and quite often, that's what's missing is resolved, and the questions are answered in a constructive way. So of course there could be cases when somebody has something against the other side, but that doesn't happen often, I hope.
My view is if you're as a designer, if I can convince myself, I can convince anybody as a designer. So it's most important as a designer because you have the faith and design is your baby. You knows that path in and out, and then you can protect it.
Exactly.
Okay, next. The next question is, a bridge requires PS1, even a small one. Should the ground hazard be fully eliminated, or can they be managed by evaluating or accepting the associated risk and the cost to the client? For example, if the liquefaction or lateral spread are expected, does the site need to be fully remediated, or the design to eliminate the hazard, or can the design only meet the client's expectable risk level? I think we have discussed this one during the presentation, and we have mentioned, and also we have shown examples that if you have you discuss with your client, and the client is the one ultimately he need to aware of the risk, that if he's acceptable risk, accept the risk, and then you can design, you can lower the requirements of that one.
I think just to add to that, Jamil, I think it's also around, we don't want any of these bridges to actually collapse.
Yeah.
So you've got to understand what is the bottom line risk that you're taking. If you try to seek a departure, and it's only going to move laterally, or it's going to drop a little bit of settlement, that kind of thing, that may well be acceptable. But if the bridge is actually going to collapse and there's risk to life, then that becomes unacceptable. So I think you've got to bring that into it all the time whenever you're looking at things like the ground conditions and liquefaction. Very often it's more about damage, but occasionally those things can lead to more catastrophic failure. And so you don't want to be putting forward a design that would incorporate that risk. But it comes down to agreeing with your client and then being able to convince either the NZTA or the local authority that that's an acceptable risk. And so there's a process to go through to arrive at that point.
Okay, thanks, Geoff. The next one, what is a suitable evaluation approach for a forestry bridge for access by a vehicle up to a 50 max?
I think if loading, then that's determined and detailed in section 7, and that's the bridge manual has been updated to cover such loading. If you're starting from first principles, Matt, you might have a better idea. I can't remember whether there was actually something specific in terms of the design load. There isn't really for 50 max. If you really want the detail, you'd be looking at the vehicle dimensions and mass.
Yeah, if you design to HN, it should cover 50 max, I think. It used to be, didn't it?
The HN more than does that. 50 max if for a longer vehicle would equate to around 0.9 HN.
Yeah, so you've either got Appendix D or typically full HN, but you could design for a specific vehicle if you wanted to, and as well. So.
On the assessment side of it, the actual material side of it, you're going to be using the material codes, or the bridge manual does have some guidance in there for particular types of bridges, doesn't it? In terms of materials, historic materials that you can use, whether that's timber or steel or concrete. what strengths you can use for those. But you've still got to work to the design codes, basically, haven't you, for that assessment of the strength of the members.
Thanks, Geoff. I think we are just running out of time. It's the last minute, so I think we'll park here. And all those questions we couldn't answer, we will provide an appropriate. If you could answer, we'll provide a proper answer and put those on our website, CSOC website. And now I would like to thank all my presenters who take their valuable time to come and present this thing. And it's not only this, it's a 1 hour, 1.5 hour presentation. There's you can see that a lot of effort and work is gone behind that one. So I really appreciate and thank you very much. And last but not least, all the audience who came here, thank you very much for attending.